Welcome back. This video is a continuation of our last lesson, so it's going to focus on refraction of light. I'm going to recommend that you read the notes, a version of these notes on Friday, May 22nd, and also found on May 26th. They'll continue on May 26th. I'm not going to get into applications of refraction and total internal reflection. That's something you can read about for the most part. So if you read on that stuff and you have questions, just fire me an email. You can find that in this textbook here. Click on that, it starts on page 14. I forget the textbook number, but file-wise, it's page 14. Just read through the rest of it. It's not that long. You'll learn about mirages and lasers traveling through different materials. It's interesting stuff. And the homework, again, with answers can be found again on the 22nd. So that should have worked out answers for you so you can see what you're doing wrong. Okay, so let's just continue where we left off from last video. Last video was about the index of refraction and the relative index of refraction as you travel from one medium to another with light. So mathematically, we're getting into it. So let's just start off with another type of question. So it says light travels from crown glass into water. The angle of incidence in crown glass is 40 degrees. What is the angle of refraction in water? So this could just be trying to figure out where light's going to travel when you go from one medium to another. If you're designing telescopes or glasses, for instance, or contact lenses or any other kind of optical equipment, you usually want to have a decent idea of what light is going to do as it travels from one medium into another. So moving forward, your little chart that I gave you in the last video, or that you should have a copy of from your notes, should tell you that the index of refraction of crown glass is 1.52 and the index of refraction for water is 1.33. Question tells you that our angle of incidence is 40 degrees, so to find the refracted angle, we're going to have to combine both of our relative index of refraction equations. We know that the relative index of refraction can be found from knowing what our second medium is divided by the index of refraction of our first medium. And then it's just a matter of plugging that into this equation and solve for our sine of the refracted angle. So we could do that, or we can just make the two equations equal to each other. And so by doing that, you end up with the first law of refraction equal to the ratio of our index refractions, and then it's just a matter of doing some cross multiplication, right? And you end up with this equation. This equation is known as Snell's law, right? And Snell's law is just looking at combining these two relative index refraction equations. So you never actually need to calculate the relative index refraction if you know a little bit more information. So the relative index of refraction is handy if either you don't know what either of the angles are, whether it's incident angle or refracted angle, and this relative index of refraction equation is handy if you don't know what your two mediums are, but at the very least you can trace the path of light. And so therefore it's handy that way. But if you know more information, like this question here, you might as well use this Snell's law and you can just skip the middleman, if you will. And that's essentially all we have to worry about. So Snell's law states that the ray of light bends in such a way that the ratio of the sine of the angle of incidence in one medium to the sine of the angle of refraction in the other medium is constant. So that's all Snell's law states. It's just a mathematical little quirk. And so starting off with Snell's law, which is kind of how I expect you guys to start off these questions. At this point of the lesson, you didn't know what Snell's law was, or at least I'll assume you didn't know what it was, and so that's maybe why you would have started with this. But I would just expect you guys to start with Snell's law. Right? In this case, you don't know what your refracted angle is, so you just manipulate it, divide both sides by the second medium's index of refraction. Plug it in the numbers, 1.52 divided by 1.33, all multiplied by sine of 40 degrees. Should give you a nice little decimal number, 0.735, something, something, something. Now this is just a rounded figure. Typically, I would recommend that you keep quite a few more. I didn't for the purpose of this videos, but usually I just keep whatever's in my calculator. And then I'd take the inverse sine function in order to find the actual angle, which in this case would be about 47 degrees. So I think it's very important to remind you that when you're doing any kind of math like this, uh, very often a lot of students get in the habit of once they get 0.7354 something, I don't remember what that number was, you'll just hit erase and then you'll only write down, some people only write down 0.7 and then do the inverse sine function, or 0.74 and do the inverse sine function. Please don't. Keep the whole number from your calculator in your calculator when you do this step right here. All right. I very much want you guys to get the same numbers I get when you're doing your math in the end. So in this case, you get 47 degrees. And that tells me that since my incident angle is 40 degrees and my refracted angle is 47 degrees, that tells me that light is going to speed up and bend away. You're going from a dense medium to a less dense medium. So if I just draw something in here casually, I didn't measure these angles, but if I draw them in casually, there's my normal line, which I didn't do a very good job making a dotted line. So my incident angle will be traveling down at that 40-degree angle, hits that boundary in the new medium, the light ray bends away from the normal, and therefore it is speeding up in our second medium, water. So let's do another math example here. So light's traveling from diamond into quartz. So diamond is very optically dense. Quartz, dense, not as dense as diamond. If the angle of incidence is 52 degrees, what is the refracted angle? So start off this question. It's basically the same question. So let's just skip a couple of steps. I've got my information from the chart for diamond and quartz. I know my incident angle is 52. I'm looking for the exact same thing here, my refracted angle. So doing the exact same methodology, I start with Snell's law this time because I know what Snell's law is. All right, I'll just solve for my refracted angle the same way I did before. Plug my numbers in the exact same way as I did before. Right, my second medium is my diamond, so I set up my equation like that, and then I'll do my math. I'll get 1.36 by the time I'm done this little process here, and then of course this is a number that just kept on going, but I just truncated after the 6, and then do the sine inverse function, and you'll probably get an undefined answer. Your calculator will either say one of many things. It'll either say error, it'll say undefined, or it'll just explode in your hand, and you don't want that. So that tells you something's wrong. A lot of people will go, oh, maybe I entered something in wrong. And then you'll just switch the 1.46 with the 2.42. And then suddenly you can get a refracted angle. Don't do that. All right. This is as expected. And the reason why this was expected is because I'm going from a very dense material, diamond, into a less dense material, quartz. And this is one of the possibilities that can happen. So I'm talking about something called total internal reflection. So total internal reflection happens when you are traveling in a very dense medium. So here's a laser, and this laser is directed into this one side here of this heavy plastic. Can't remember what type of plastic this is, but this is just a little plastic in the shape of a, I guess, shockwave flash S shape, if you will, leaned out S, if you will. And it enters in, they shine it in, so it's going basically down the normal line and this side here. But when it gets to this boundary right here between the air and this plastic, the angle of incidence is too great. And when the angle of incidence is too great, when you're going from a dense material into a less dense material, this air here where the mouse is, there is a possibility that light will not escape at all. So when that happens, light does not escape, no refraction occurs, and light just reflects inside the medium. Same thing happens here, can't escape here, and so it just reflects. And as you see, as it comes out here, it's hitting the end of this thing, basically down the normal line. This is cut off straight edge here. It's almost perpendicular to the surface, and whenever light travels perpendicular to the surface, it should escape. Unless it's, of course, a mirror, but we're talking about transparent materials here. So this light should escape, scatters a little bit, and you can see how it scatters and makes a big, big mess over at the end here, but it does escape. It doesn't escape there, doesn't escape there. And that's because it suffers from total internal reflection, right? So inside here, no refraction occurs, only reflection. So this little diagram I stole from the physicsclassroom.com. If you shine any laser light or just light in general straight down the normal line, so here it says 0 degrees, so that's just implying that light is traveling down the normal line. If you travel down the normal line, 100% of the light should actually pass through. Well, almost 100% of the light. There will be some backscatter, but almost all the light's going to transmit into the new material. When you have a slight angle, so in this case it's 15 degrees to this imaginary normal that's not visible, you're going to get a little bit of reflecting light, right? Because you're always going to have some light reflect at the surface, but you'll have a bit more than you did at zero. So some light is going to escape to this faster medium, and with this faster medium, light is bending away from the normal line. So you can see at a 15-degree angle, it refracts at a 20-degree angle. As you increase that angle a bit more, 30 degrees angle of incidence, let's just imagine it refracts at 42 degrees. So it's going to bend further away from the normal. At 45 degrees, you get even more bending. You have 70 degrees, and you'll notice the reflected beam gets darker and darker and darker still. And at some point between 45 and 60 degrees, what's happened is this light has refracted to the point where it's just technically along the surface of the medium. And when it refracts on the surface of this medium, it just stops refracting, and 100% of the light actually goes back in towards the reflected ray. And so that's why this little green light, it's not that it changes colors, it's just this little green light here is just your reflected ray back into the original medium. This only happens when you go from a dense material to a less dense material, but it has to be greater than some critical angle, because you can see in this little example, in all these examples except for the last one, light was able to escape every single time until the incident angle became too large. So what's being described is this, essentially. If your angle of incidence, so this is just an example between water and air, if your incident angle is not overly large, it should refract in the new medium. But then there's this critical angle where once we reach this larger angle of incidence, technically the light would refract along the surface. So we would say at this critical angle, this very necessary angle, we would set a refracted angle to 90 degrees. And from there, we can calculate what that necessary angle of incidence must be. If your angle of incidence is anything larger than your critical angle, no light will escape, and all you'll get is something called total internal reflection. Okay? So again, total internal reflection will only happen if you're going from a dense material to a less dense material. It cannot happen the other way around. So if we go back to the question that we're working on, the last one with a little dog meme, light traveling from diamond into quartz, if the angle of incidence was 52 degrees, what is the refracted angle? Well, we got an error when we tried to calculate it. And so that error basically tells us that there is no refraction, only total internal reflection, right? And I can definitely tell that there can be total internal reflection because my index refraction number 2 was less than number 1. So this isn't the only thing that has to happen, right? I could have said this is only 10 degrees, and if that's the case, if this angle of incidence was 10 degrees, light probably would have escaped, and I probably would have gotten a refracted angle. So we just basically need to know, in order for it to potentially happen, N2 must be a smaller number than N1, and then it's possible to have total internal reflection. So instead, let's maybe calculate the critical angle. What angle would we stop getting any refraction? And that's all the critical angle is asking for. So it's looking for the critical incident angle, because at the critical angle, we know that our refracted angle should be technically 90 degrees. And so when we follow Snell's law and input in our critical angle, technically sine of 90 is 1. So effectively, we can just get rid of this sine r on Snell's law when we're solving for the critical angle. So it basically takes Snell's law and makes it look like this, but when we're trying to find the critical angle. Okay. So again, we only do this if we're going from a dense medium to a less dense medium and solve for the critical angle. So divide both sides by N1, and you've basically got N2 over N1, which we know is our relative index of refraction between the two mediums. So that was the previous video. But if you want to find the critical angle and we're going from a dense medium to a less dense medium, you can just take the inverse sine function of your relative index of refraction, and that should give you your critical angle. So in this case, I'll plug in the two numbers. You have quartz divided by diamond, so 1.46 divided by 2.42, and you'll get some kind of decimal number, which is great. If you got a number that was 1 point something or other, then you've definitely got a mistake somewhere in there, or you'll probably want to calculate a refracted angle. You're definitely not solving for a critical angle at that point. And then you just take the inverse sine function of what you have, and your critical angle is about 37 degrees mathematically. And so basically what that means is if your angle of incidence is greater than 37 degrees, 37.1 specifically, no light is going to refract, and all you're going to get is total internal reflection, often abbreviated just as TIR, if that's how you pronounce that. If my angle of incidence was less than 37 degrees, I would have refraction normally, right? Light would escape and go into the quartz, right? But after 37.1 degrees, no light escapes. We have total internal reflection. So there's some quirks with this apparently. And this is where if we were in class, I'd show you some examples with some fiber optics that I just have lying in the back room, and give you a chance to play with some lasers as well. But here we are in the world of YouTube. One thing that I think a lot of you guys might be able to relate it to, if not now, maybe in the future, are diamonds. So diamonds are apparently really pretty to a lot of people for the reason of total internal reflection. So if you kind of gaze at this little fake diamond here drawn in, because diamonds have such a large index of refraction, any light that enters in through the top, so there's a reason why they're cut the way they're cut, any light that enters in through the top will not escape out the bottom. So it's coming, if you focus on this little red diagram here, any light that comes through here, you're going to get refraction at this boundary here, so it bends a little bit, right? But then when it gets to that point right down here, no light is going to escape out the bottom. And so it reflects, and the way this is angled, it hits there. So again, we're just talking about the light hitting there, and it's going to come straight back out the top. All right, so big deal. What does that mean? Not much. It's pure white light. It's going to reflect, in this case, come back out as white light, but in the opposite direction, coming straight up. But any light going through the very top here, you know, hits close to where I was at that red spot there. It's going to reflect at this point here, and right, because it can't escape there. But when it hits out the edge here, this is often cut into a lot of tiny little angles here to help the light escape. And when it does escape, it's going to undergo dispersion. So dispersion is when you have refraction, but light is separating into all the colors of the rainbow, right? Roy G. Biv, if you will. And this is the reason why diamonds will sparkle. So you're going to get total internal reflection, but as it refracts back out, another phenomenon known as dispersion happens, and it looks pretty. And then most people go, ooh, I want one of those. And obviously it costs an arm and a leg. So when it comes to diamond, diamond has a relatively small critical angle of 24.5 degrees. Most substances aren't as small as diamond. And so because it has such a low critical angle, not a lot of light is going to find places to escape. And so this is a slightly better version of it. So whoever went through the trouble of doing the computer animation showed that as light is traveling down, you get a little bit of reflection as it first goes from one medium to the other, because that's typically what's going to happen. But then if you really want to see the path, you can pause the screen if you really want now. You'll see it light come down here. It doesn't escape, total internal reflection, go straight across there. Again, doesn't escape, total internal reflection. But as it comes back up here, it goes back out the very top. Some of the light, of course, escapes and refracts normally, but of course, some is going to reflect back down because you're not going to get 100% light transmittance. Some of it will reflect back in, but then we have this process of it being trapped inside as it bounces back and forth, back and forth, back and forth, until it can finally escape out of that end or maybe even that end. But it takes quite a little bit of bouncing around back and forth of total internal reflection. And the whole time doing that, you end up with a little bit more dispersion with every single reflection. And as you can kind of see from this little still picture, it becomes quite colorful, and therefore people go, ooh, pretty, I want. So that's one of the reasons why people love diamonds so much. Diamonds are also one of the hardest substances out there, which makes them great for drilling into the ground. So they have a gem quality to it, and they also have an industry quality to it. And if you recall, diamonds are nothing but just pure carbon. So chemistry, figure it out. I'll stop there because I could probably go on for a long time and get into prisms and all sorts of fun little shapes that you can do with. But I think that stuff you should probably just try on your own mathematically. Um, again, do read the textbook on the 22nd date and again on the 26th. In fact, you should just read the entire little bit of the textbook. It gets into things like mirages and how light bends for going from one medium to another. It's rather interesting. I'll stop the video here. Thanks for watching. Email me if you have questions.